So here comes Emma.
Good evening, everybody, and thank you for coming. So tonight I'd like to talk to you a bit more about gravitational waves. So back in February there was a big announcement that gravitational waves were detected for the first time, and this was very exciting. So I'd just like to start off my talk with explaining what a gravitational wave is. So in 1916, when Einstein was coming up with his theory of general relativity, he actually started to think about what gravity was, and he thought about it in a different way to Newton. And what Einstein actually proposed was that massive objects, and just to clarify, a massive object is something that's very, very heavy, and it doesn't necessarily have to be really, really big. But that massive objects would actually bend space and time. And this is an image depicting that, and actually that how much the space-time is bent is what we call gravity. So if you can see here, there's a dip in the space-time created by a massive object. Things in the universe tend to move around, just like the moon orbits the Earth and we go around the sun. Well, that means all these curves and bends of dips are moving around with these objects, and ultimately you're going to get overlaps, and this causes ripples to form, and it's these ripples that we call gravitational waves, and these are analogous to ripples in a pond. And I have a demonstration here which explains or shows how massive objects can bend space-time. And if you see here, I've got a little animation, and this is a computer-generated gravitational wave. So the wave itself is propagating from the back here towards the front. And if you look at the hoops, they're being stretched and squashed. And this is exactly what happens to the space around us as a gravitational wave passes through. So now we know what a gravitational wave is. How do we make them? So there are two requirements that need to be fulfilled. The first is that we need some asymmetry. And this is something that I think isn't very obvious, and it can be a bit difficult to understand. So I'll explain it to you how I understand it. If you have a sphere or a ball, and let's just say for argument's sake that it's black and it's matte, so light doesn't bounce off it. If that ball is spinning, if you're looking at it, you can't actually tell if it's spinning. So from your perspective, nothing is changing in time. So if you take this perfect sphere and it's spinning and you drop it in a pool of water gently, you'd actually find that it doesn't create any ripples, it just spins. So if we deform our ball, and let's say we make it pear-shaped and lay it flat and spin it, you would actually see that something's changing, so spinning would happen. And then if we drop our pear into a pool of water, that would actually create ripples. So it's like this deformation is hooking on to space and stirring it up and creating these ripples, and that's exactly how gravitational waves are made. So that's easy. There's lots of asymmetric objects everywhere. I'm asymmetric, my hands are, so as I move my hands, I am in fact generating gravitational waves. But the problem with gravity is it's incredibly weak. So I actually took the liberty of calculating my gravitational potential, and it turns out that it's 100 millionth of a metre is the distance you'd have to be from me to experience it. So you pretty much have to be touching me before you could be attracted. And at that scale, the other forces the other forces actually take hold. I didn't expect that to invoke laughter, sorry. So electromagnetism would actually become more important on this scale. So to overcome this, we actually need lots of mass. So what objects do we have in our universe that are massive enough, that would have a strong enough gravitational potential to create gravitational waves that we could detect? Well, one of the answers is something that I think everybody's heard of before, and that is a black hole. These are the most densest objects known to us in the universe. To give you an idea of how dense they are, if you took 2 of our suns, squashed them down and squeezed them into the size of Southampton, that would make a black hole. And the gravitational potential of a black hole is so strong that if light experiences it, it cannot escape from it, and this is why they're black. But there are also other objects in the universe that could be gravitational wave source candidates, and the other one is a neutron star. And these are really interesting objects. So again, they're incredibly dense. These are the most compact known star that we have in the universe. To use the same analogy, if we take 2 suns and compress them down into the size of Birmingham, that would create a neutron star. And just as a scale to compare to the black hole, Birmingham is twice the size of Southampton. So a neutron star is half as dense as a black hole. A neutron star, unsurprisingly, gets its name because it's made up mostly of neutrons. And they have incredibly strong magnetic fields. The strongest magnetic field neutron star we know is called a magnetar, and the magnetic field is 1 billion million times stronger than the Earth's magnetic field. And because this is such an extreme environment, it's a really good way for physicists to test the laws of physics. Because you've got the intense gravity and matter starts to go a bit weird inside neutron stars. So they're very interesting objects. So I hope now that I've convinced you that we have objects that have enough mass in the universe for us to create gravitational waves that we can detect. But I haven't covered the asymmetry aspect of it. So gravitational wave sources actually come up in 4 different categories. And the first one that I'd like to talk to you about is binary inspirals. And so when you have 2 black holes or 2 neutron stars, or a black hole and a neutron star, and they orbit each other, the orbit won't be circular. So this is how we generate the asymmetry. And so I've got a video I'd like to show you. Thanks. So this is an animation of 2 neutron stars that are in orbit around each other. These swirls that are coming up here is the gravitational wave radiation, and this process happens over millions and millions of years. But as they're losing energy being radiated away in gravitational waves, they actually spiral in towards each other, and because the distance is getting smaller, they actually spin up and get faster until they eventually collide in a cataclysmic event. So what researchers are actually doing is they're calculating what the gravitational wave signal looks like at the moment that 2 neutron stars or black holes merge. And what they do is they use this information so that when data's coming in through the detectors, a computer tries to see if this signal that we've predicted is in and amongst the data. And if it is, alarms go off, as they did on the 14th of September last year, and a detection has been made. The next type of gravitational wave source that I'd like to talk to you about is something that we call continuous sources. So a continuous source would be a spinning neutron star. They are called continuous because a neutron star spins at, as far as we're concerned, a very consistent rate. So the signal that we receive is very much like a singer holding a note. But the neutron star needs to develop some asymmetry. And one way it can do this is by growing mountains. And this is actually what my research is on. So I've got an example of how a mountain could be made. So this is an animation, and so the orange blob is a star very much like our sun, and it's orbiting a neutron star. And because the gravitational field is so strong of the neutron star, it actually draws matter from the sun-like star towards its surface. And you get this disk form around it of the matter, and matter will actually fall onto the neutron star. A lot of this matter will actually be burnt, and that's what we're seeing with these jets, is radiation coming off. But also some of it will fall onto the surface. And because neutron stars have incredibly strong magnetic fields, it can actually guide this matter down the magnetic field line. So you get regions of more build-up than others. And this is how essentially mountains can form on a neutron star. Another way how neutron stars can develop some asymmetry is when their spin becomes unstable somehow. And what this happens is it causes the shape of the neutron star to actually change. And the best way I can explain this is when you are driving in your car, if you go around a roundabout a little bit too quickly or around a bend a bit too quickly, if you're turning to the right, your passengers will all swing out to the left. And that's because the forces are pushing them outwards from the direction of travel. And that's what happens with neutron stars, so they can change their shape and become wider at the equator. So then the asymmetry condition is satisfied and gravitational waves can be formed. So now I'd like to go on to the next category of gravitational wave sources, which is the stochastic, here we go, which is the gravitational wave stochastic background. And this is very similar to the cosmic microwave background, which is the light imprint left over from the Big Bang. And back in the day before digital, if you were trying to tune in your TV and you'd get all that white noise, that was the cosmic microwave background radiation that you were actually picking up. So what happened was, just after the Big Bang, we had this quantum gravity era. So we had a quantum soup, and quantum's just the scale that we're talking about, which is very, very tiny. And we had like fundamental particles, gluons and quarks. And then shortly after this, the universe went under a second rapid expansion, which we call inflation. And this actually acts as a magnifying glass of this quantum era, so that today we should be able to see the gravitational wave imprint left over from the Big Bang. And then we've got the final category of gravitational wave sources, which we call burst sources. Now, these are quite interesting because they're different to the other sources that I mentioned earlier. So pretty much daily we observe light emissions which appear to come from big explosions at different various points in the universe. But we don't necessarily know what is causing these explosions. Supernovae is one candidate of the source, but that doesn't explain all of them. So what we will be aiming to use gravitational wave astronomy for is to understand what these sources of gravitational explosions in the universe are. So where researchers are using the in-spirals and the continuous sources, we'll take that knowledge, filter it out, and then we'll just be able to get the raw gravitational wave signal from these bursts. And we believe they would have a gravitational wave signal because they are such violent events. So who knows what we'll be able to find. So that's the 4 categories of gravitational wave sources. So you could say we have a spectrum of them, which leads on quite nicely to my final slide, where we have the gravitational wave spectrum. And it's just like the electromagnetic spectrum, where you have light ranging from gamma rays to X-rays down to microwaves, and how we have different telescopes to see these different wavelengths of light. We actually have gravitational wave detectors that will enable us to see different gravitational wave signals depending on how long they last for. So the ground-based interferometers are on the millisecond range, and this is what we detected with the black holes back in September. And there are plans at the moment and experiments underway to put one of these detectors in space. And this will give us a we'll be able to detect signals on the second to hours range. So what does the future of gravitational wave astronomy hold for us? Well, the truth is we don't know. We're opening our eyes to the universe in a totally new way for the first time. And that's the beauty of research, and that you never know really what you're going to find. So I'd like to end my talk on a note, which is a quote from one of my favourite physicists, which I think sums up why we do this. And it's Richard Feynman, and he said, "Physics is a lot like sex. It has practical reasons, but that's not why we do it." Thank you for listening.
Thanks, Emma. That was really good. And I think points for saying cataclysmic event after a few pints and getting it out almost perfectly. So yeah, any questions for Emma from the audience? So, okay, I'm curious. So you were talking about the gravitational wave spectrum. So are you quite looking forward to seeing pictures in gravity waves, as in actually taking pictures from the Earth?
Yes, but it doesn't quite work like that in the same way that light does.
Does it not? Okay, so I'm not going to get a gravity wave camera anytime soon then?
No, the best way to explain it is that the gravitational wave spectrum is the soundtrack to the universe, because we've already got the light and the signals are actually in the audible frequency, so we can convert them to sound, which is why Ian was able to play the gravitational wave chirp of the coalescing black holes that was mixed into that funky song.
Wow. So, yeah, because I actually thought that when you heard the chirp, it was actually transposed, so it's actually audible frequency. So that's quite cool. I'm looking forward to listening to the universe then. Sorry, we have a question here as well.
I was going to get something like the cosmic microwave background picture in terms of gravitational waves. So, like a map from the whole universe coming to us, something like that, or it's...
Yes, we should have a map of the gravitational wave signature. I'm not entirely sure what it would look like, but the equivalent, yes.
Must be really exciting. Sam's got a question.
Does the amount of asymmetry change the size of change the wave in any way, change the gravitational wave, the amount of asymmetry?
Yes, it does. So it would create a larger amplitude.
She's going to do it. There's going to be supervisor discussions here later. There's a thumbs up. Everything is okay. Oh, we've got a question back here.
Why do you differentiate between the signal coming from the continuous source and
Very good question. So the continuous source, because it is so repetitive, it's very clear, it's very easy for us to predict. So what we'd actually do is we'd remove the continuous source and then see what's left in the data, and then we'd work with that. So that would then...
This table over here.
So when you put your excitation to space, you can't have one, you have two, and emission, or laser emission. To get the distance between the detectors and mirrors.
So I believe they're actually having 3 arms in the space detector, so that would give us a broader view of the universe.
And what sort of distance are you talking about between the mirrors and the source?
Mirrors in the source, well, it could be as big as the observable universe, depending on where the source it's coming from in the universe.
If you're putting a detector out into space, somewhere in our region, then you're going to have a certain distance, a minimum distance between your source and your mirrors.
So I think if I understand the question correctly, the gentleman's asking, how do the distances in, for example, the LISA experiment compare to the distances involved in the interferometer arms in the LIGO experiment? So the nearer to source distance in that case.
Oh, excellent question. I'm afraid I don't know the answer.
I'm sure there will be someone in the room though who does know the answer, so come and approach us later, and yeah, we may well be able to help you. There's a question on this table over here, I noticed.
Hello, I was wondering about neutron stars when you say that they can collect mountains. I was under the impression that neutron stars are really, really smooth. If they collect all this stuff, can we know, do they keep the mountains or does it just go back to being a small surface? Or is it spat back out?
So this is exactly what my PhD project is on. So the idea is that the mountains could theoretically be built. When I say mountains, we are talking about 5 millimeters, but they are, because neutron stars are so dense, that is significant enough for a gravitational wave signal. But the thing is, how long does that mountain live for? And if that accretion process goes on long enough for a mountain to build up. But nature likes to make things very smooth, as you say, so it's kind of a battle against nature's default position.
So me and Matt were actually debating that in the office this morning and wondering what was happening, and so that's a really good question. Well done for asking it, and I'm quite glad that there are people like Emma doing PhDs on this thing to find out for us. But yes, question here.
Why do neutron stars send a jet of material out from their poles?
Oh, okay, that's a good question. So because you've got the magnetic field, I'll bring up a picture. Oh, sorry. So the question was, why does the neutron star spew out the burning that I said from the magnetic poles? So this is the neutron star. These represent the field lines of the magnetic field. And because the magnetic field is so strong, it actually channels the electromagnetic radiation towards the poles, at which point it spews out. So this acts to repel the matter down to the poles, and that's why it gets focused.
So it's material coming in and missing and then going off at the poles?
No, it's kind of channeled along the field lines and then it burns.
So it's the radiation that's going out?
Yeah, it's the radiation. Oh, I've got the answer for the Lisa question. It's 1 million kilometres. Thank you, Alice.
Told you someone would know. And does Lisa still have funding? Is that still going to go ahead?
Yes, it might even be brought forward because they've put up a test at the moment and it's been very, very successful. And the test was to see if our technology is currently advanced enough for the programme, and they might be bringing it forward by about 5 or 6 years.
Wow, it's so good when science works. A bit like this evening, really. Any more questions? Oh, another question from Miss Sable.
When you talk about the radiation coming out from the poles of the neutron star, what is forcing that energy outwards?
Alice, do you want to...
We have a volunteer out here to come and answer this question admirably.
So it's kind of a bit like what happens on Earth and the like the aurora and stuff. So essentially the particles getting channeled by the magnetic field. So they get channeled onto the magnetic poles and then they get thrown out again.
Why does it get thrown out?
Because there's so much energy.
Yeah. Again, I'm not entirely sure about that, but it is to do with the channeling of the particles by the magnetic field. Yeah.
Maths doesn't like blowing up, so when maths gets too big and we start to go to infinities in physics, then something else tends to happen and things tend to go away from infinities, or go towards them really fast. Either way, infinities aren't good. Any more questions in the audience? Fantastic, I think that's a no. So we actually have the panel discussion and Pint quiz down to start at 10 o'clock. All our speakers have been really good on time this evening. So, including Alice, and I'm sorry, Alice up here speaking and answering the question so admirably, but including Emma, you've been fantastic. Thank you very much. Everybody, thank everybody. Yeah, and we won't have too long a break, and then we'll be back for get all the scientists up here.